only operators that can appear, you can start writing down 3-point functions in superspace and construct all of the different possible 3-point functions in superspace that are compatible with superconformal symmetry. And then you see that you have solutions corresponding to these different classes of operators. Okay, so now, okay, this is the form of the OPE. You can now write down the crossing symmetry conditions. And okay, I get a sum rule which involves all the operators in the phi dagger phi OPE. OPE coefficient squared times, let's write this curly f vector of u and v, where these are related superconformal blocks. You also get a contribution from the phi cross phi OPE. Non-curly f equals 0. And actually these guys are just related to conformal blocks. The reason is that in the case of this phi phi OPE, these are the only operators in their given supersymmetry multiplets that have the right R charge to appear in the OPE. Okay, there's no other operator in this O's multiplet that has the same R charge as Q R squared O. So the superconformal blocks is reduced to conformal blocks. Okay, so now that you have this set up, you can start producing bounds. This is some vector of some once again. And start producing bounds. So one thing you can do is bound the dimension of the leading non-chiral operator in phi dagger phi as a function of the dimension of phi. Right now we're in 40, so a free scalar starts at 1. In a free theory, dimension of phi dagger phi would be 2. And if you compute this bound, you see a curve like that. Everything above this line is excluded. Okay, the thing that's staring at you in the face is that there's something that looks sort of like a kink here. And this is currently a mystery. So, so we don't know if there's a theory living in this kink, and if there is, what 4D n equals 1 SCFT is it. So this has now become a very interesting problem because this looks on the surface very similar to the story that played out with the 3D icing model. And you might hope that, okay, if you keep pushing things further and further, maybe instead of this bound, we come up with some small island around this point and then shrink more and more, and we really just hone in on some new solution to crossing symmetry. So we haven't done that yet. That requires going to, a system of correlators containing phi dagger phi and phi. And that's a case where not all of the superconformal block structure has been worked out yet. So that's something we're currently working on. But actually, even in this simple context with just phi dagger phi, we can start to learn a lot of information about the properties of the theory living here. So that's what I want to tell you about. So first of all, okay, where does this occur? So I said this was at 1. This is something like 1.41. And this is about 3.2. So now we can ask, is there some sharper way to characterize what's going on at this transition? And actually, it turns out that there is. So another plot we can make is to look at bounds at OPE coefficients. And in particular, let me look at the bound on the OPE coefficient of the phi squared chiral operator appearing in the phi OPE. Okay, so, and in fact, this is a case, because there's a sharp separation between this operator and all these other scalars that can appear in the OPE. In fact, there's a dimension, a gap in the dimensions that's forced by this unitarity bound, so this is really isolated as long as delta phi is less than 1.5. We can place both upper bounds and lower bounds on this OPE coefficient. And that's something that you can do. So you get some upper bound. You also get some lower bound. And, okay, so first of all, as you approach, delta phi goes to 1. Both of these bounds approach the same value, and this is, in fact, the square root of 2. Why is this the square root of 2? Well, here in setting up the bootstrap, we've assumed all our operators have some canonical normalization. And in a free theory, the canonically normalized operator is 1 over root 2 phi squared. This is the operator that has a 2-point function with a 1 in it, just because there are 2 different ways to do Witt contractions between phi squared and itself. So the phi plus phi of PE contains root 2 times this in a free theory. So that's why we see root 2 here. And the other interesting thing is that there's an upper bound, but there's also a lower bound. The lower bound goes away at some point, and the point at which it goes away is the same value, 1.41, as we saw over here. So this is the first dimension at which the phi squared operator can decouple from the spectrum. Okay, below this dimension, you have to have a phi squared operator in the spectrum. This is all excluded. But this is the first dimension at which it can go away. So, so it's natural to guess that delta phi squared is 0 for whatever theory lives in this kink. Okay, and we can ask the question, is there some minimal, quotes, SCFT with phi squared equals 0. I should also say that if you go through the exercise of reconstructing the boundary solution, I told you how to do this for the IC case. You reconstruct a solution living along the boundary. You, in fact, do see the phi squared operator decoupling as you approach this point. Okay, so that's sort of puts more, makes this story more believable, I suppose. So okay, so we can now start making plots assuming phi squared is constant. So for example, let's go back to this plot. What happens if we assume there's no phi squared operator? We plot the region. Well, you can see over here first of all, one thing that has to happen is that everything to the left of 1.41 has to be excluded. And that's what happens. So everything to the left of this dashed line is excluded. And everything to the right of it is still not. So that what happens is precisely what you expect from this plot. Another question we can ask is if there's a theory living here, is it a local And what do I mean by a local SCFT? Well, one property that you expect of local theories is that they contain a stress energy tensor. Okay, for all the charges in the theory, there's some local conserved currents. So what I actually mean by this question is, does this solution contain a stress energy tensor? And okay, to probe that, first of all, in 4D n equals 1 theories, the stress energy tensor is contained in a multiplet with the U1R current. And the U1R current is the superconformal primary operator that appears at the lowest component in this expansion. So really what we have to do is bound the first spin 1 operator and ask, is this first spin 1 operator in U1R current? So if it were a U1R current, it would have a scaling dimension of 3. And so we can make this plot assuming this relation over here that phi squared equals 0 and ask what is the allowed region in delta phi delta spin 1 space. And okay, so first of all, everything, because of this assumption, everything to the left of 1.41 is excluded. But there's also some upper bound on the dimension of this operator. And the interesting thing is that you see this upper bound going precisely to 3 right at this minimal value, 1.41. And everything out here is also excluded. So we could turn this around and say, okay, if you want to ask about the theory living here, then this bound tells you that it must contain a U1R current. Okay. And consequently, a stress tensor. So right at this point, a U1R current is required. So now that we've established that there's a U1R current and hence a stress tensor, we can also ask about the central charge of the theory, which shows up in the coefficient of this operator. We'll ask about the central charge. Okay, so this shows up in the OPE coefficient between phi dagger phi and let me write it as J sub R, the U1R current. And this is proportional to delta phi squared over C. Yeah.
Okay, 100 assume phi square equals 0.
Yes.
How would the plot have to,
To the left of 1.41. So it looks very different. So first of all, the free theory is allowed. So it so I think it just looks something like this, where it starts at the 3 value and goes up, but no, there's no obvious features in it.
So there are, we could write down the models for phi given scope potential. So imagine you lie between those two. Where do they lie?
The Escamino models don't flow to interacting with these points. Right. So in the infrared, they just float to free theories.
Maybe.
Okay. as I said, because of there's a word identity which relates this coefficient to the phi-Dagger phi 2-point function coefficient, which picks up the factor of the dimension phi, and then because of the normalization of the UNR current, the factor of C. And we can also make this play this plot assuming phi squared equals 0. And so the left one is excluded. And in general, you can compute some lower bounds on the central charge. Also, if you assume that there's some gap in the spectrum between the UNR current and the next spin 1 operator, we could compute an upper bound on the central charge. And the precise form of that upper bound depends a bit on the gap that you assume. So assume delta B prime, delta J prime is bigger than 4, you get some stronger upper bound. If you assume delta J prime is bigger than 3.1, you get a weaker upper bound. But in all of the cases, the upper bound converges to the same point as the lower bound at this minimal limit. So this is C. And in the normalization convention I'm using, this is going to central charge of 0.1. And actually this is a fairly, well, it's a pretty small value, but it's bigger than the central charge of a free chiral operator, where C free chiral is 1 over 24.
So just for orientation purposes, where would like a super QCD-like theory fit on this?
Good. So super QCD theories, their central charge depends on NF and NC.
Yes. So suppose I take it as low as possible.
Right. So they're all bigger than 1
In your normalization. Right?
in this normalization. So this is about the central charge of, this is a little more than 2 free chiral triplets. But in SQCD theories, there's also some gauge contribution to the central charge, and that tends to be fairly large, which always pushes it above 1. I can also say in 4D-1 theories, the central charge is related to the UNR anomalies. So this is how you can calculate it in lots of different theories. And in this normalization, it's 1 over 32 times 9 trace R cubed minus 5 trace R. Okay, so this is fairly small. And the last thing that we've done so far to try to understand the properties of this theory is really try to study more carefully where these numbers are converging to as we push the numerics farther and farther. So, for example, you could ask the question, okay, this is 1.41, could it be the square root of 2? It's fairly close. Could this be converting to any interesting number, and so on? So we don't have a rigorous answer, but we can pick out this is a unique point in delta phi C space, which we can compute at different levels of numerical precision. So we push the search space of the functional to be bigger and bigger by including more derivatives. And so as you increase this cutoff in the number of derivatives, you get some sequence of points in delta phi C, which corresponds to this point. And so this is what happens as I increase the cutoff. which I called lambda before. And okay, so this starts at 1.41 and 1. And okay, we've pushed it. We pushed it. To more and more derivatives, and we haven't quite seen convergence yet. But you could try to do an extrapolation of where these points are heading towards as you try to go to an infinite cutoff. And at least if you do a naive linear fit in 1 over lambda, we get that they're converging to something like 1.428 minus 0.441 over lambda, and 0.111 minus 0.642 over lambda. So this is our best guess for where this unique point is converging to. It's not rigorous because it's based on some extrapolation, but we get a fairly good fit. And actually, this is kind of intriguing because 0.111 looks like a rational number that we all know and love, which is 1/9. So we have a conjecture that if this theory exists, that C could be 1/9. We could also you could squint at 1.428 and guess maybe this is 10 cents, which is the simplest rational number we could find that is close to 1.42. Okay, so this is somewhat speculative, but this is a very concrete puzzle right now. Is that we see all these features in the bootstrap, which looks like there's probably some real solution living there. To rigorously establish that, we'd want to go to systems and mixed correlators, see if there's some small island around this point, see if we can really reconstruct the solution, and check if it passes all the tests that we can come up with. But at least right now, it seems at least plausible that there's some theory living there, and maybe it has nice rational values for the central charge.
What is the lowest central charge? Lowest central charge theory equals only CFT. We need apart from possibly this one and the one.
So let's see. So basically all 4D n equals 1 gauge theories that I know about have central charge bigger than 1, like SQCD. There are also so the closest I've found are things like Argyris-Douglas theories, non-Lagrangian SCFTs. So for example, the simplest n equals 2 Argyris-Douglas theory has central charge 11/30, not a third. And I believe there are n equals 1 deformation. There's an n equals 1 deformation of it that has central charge 1/6. But that's the smallest n I'm aware of. So I don't know of any theories that like this. Okay. In the last 5 minutes, let me tell you about one other story we've been developing in Bootstrap, which involves fermions in 3 dimensions. So I don't have time to explain the whole setup, but of course, in general, it's very interesting to extend this to 4-point functions of operators with spin. Okay, we'd like to do the Bootstrap for currents and stress tensors, and all sorts of spinning operators. This is one of the simplest examples of that, and it's one that we've now gotten working. Of course, once you you're talking about operators with spin, you have the added complication that there are multiple tensor structures, both in the 4-point function and in the 3-point functions. So you have to contend with that. But that's something that you can do. You can sort out all the tensor structures and write down all the crossing relations for them. So let me basically skip to the punchline. So we've set up the crossing relations for 4-point functions of a Majorana fermion in 3 dimensions, 2-component spinners. The psi OPE, let me also say, we're assuming there's a parity symmetry. So you can divide the operators in the psi OPE into parity even operators and parity odd operators. And so there's some set of parity even scalars, including the identity, and other parity even operators. And there are also parity odd operators, which we'll call sigma, even, odd. So we've managed to compute bounds on both the leading parity even scalars and the leading parity odd scalars. So if I bound the leading parity even scalar, what happens? So you see this curve. A free fermion in 3 dimensions has a dimension of 1. And in weakly coupled theories, you expect an operator like psi bar del/psi, which is parity even, and has a dimension approaching 3. On the other hand, if you track this bound, you see some sort of kink in it, starting around 5.1 and 1.27. And this is another mystery in the bootstrap right now. We don't know how to interpret the fact that we see some discontinuity here. Actually, if you look at the parity odd operator, leading parity odd operator, this typically has a lower dimension, okay, because the leading parity odd operator is, in the free theory, is psi bar psi, fermion master. So this starts at 2. And okay, if you track this down out to this value of 1.27, something else very interesting happens, which is that there's a sharp jump in the bound. So there's all this. This is excluded. This is excluded. But what you see is that this is the first dimension where you can have a big gap in this parity odd spectrum. And this is actually a very, at the level we've pushed things so far, this jumps up to like 7.5. So it can be very, very decoupled at this point. So let me just leave you with this mystery. So we can ask a very sharp question. Is there a 3D CFT with a fermion dimension of around 1.27? And you can see that if there's some theory living up here, the parity odd scalar is decoupled, the parity even scalar has a dimension of around 5. And